Maths Paper 1 made the headlines in 2023, and not for the right reasons. If you want to learn more about this paper, then you've come to the right place. In this video, I provide clear, concise, and colourful solutions to each and every question. If you've recently attempted this paper, you can use this video to check your work and see detailed solutions for any of those troublesome parts you had difficulty with. For those of you who are preparing for your own Leaving Cert, the fact that so many students struggled with this paper provides a unique opportunity. If you can master the skills and knowledge required to tackle this challenging paper, then you'll be well equipped for anything that might be thrown your way. In question 1a, the vertical bars represent the absolute value. This means that we should take the positive version of whatever number is inside. If we want the absolute value of 5 plus 3m to be 11, there's two options. Either the 5 plus 3m is equal to plus 11, or the 5 plus 3m is equal to minus 11. We can solve for m in both these cases. Let's start with 5 plus 3m is equal to plus 11. To begin, I'll subtract 5 from both sides. Then we'll simplify on the right-hand side. Next, we divide both sides by 3, and then we get our answer. M is equal to 2. We can solve 5 plus 3m equals minus 11 in a similar way. We subtract 5 from both sides. We perform the calculation on the right, and then we divide both sides by 3. This gives us m is equal to minus 16 over 3. In part B, we're given an equation and asked to express k in terms of h and j. This will involve performing algebraic manipulations to the equation until we've isolated k by itself on one side. Fractions are a bit awkward, so it's a good idea to get rid of them. I'll do this in two steps. First, I'll multiply both sides of the equation by j plus k. Then, I'll multiply both sides of the equation by h. Since we want to isolate k, it's a good idea to group all the k terms on one side of the equation. We can do this on the right if we subtract k from both sides. Now, we can factor out the common k on the right. As the final step, we divide both sides by h minus 1. This brings us to our final answer. K is equal to j over h minus 1. To solve part C, we can use the fact that a cubic term can always be written as the product of a quadratic term and a linear term. In this question, we're given the cubic x cubed minus 2x minus 3r. And we're told that the quadratic x squared minus px plus 1 is a factor. Using our fact, it follows that we can write the given cubic as the given quadratic multiplied by a linear term, ax plus b, for some a and b. The strategy here will be to multiply out the brackets on the right-hand side and then match coefficients with the cubic. The brackets multiply as follows. X squared times ax is ax cubed. X squared times b is bx squared. Minus px by ax is minus pax squared, and minus px times b is minus pbx. 1 times ax is ax, and 1 times b is b. From here, we can simplify by grouping like terms. The only x cubed term is ax cubed. There's two x squared terms, bx squared and minus pax squared, so the overall coefficient for x squared is b minus pa. There's also two x terms, minus pbx and plus ax, so the coefficient for x is minus pb plus a. Finally, there's only one constant term, plus b. The cubic that we were given was 1x cubed plus 0x squared minus 2x minus 3r. We can match the coefficients to obtain four equations. Matching the x cubed term gives us a equal to 1. Matching the x squared term gives us b minus pa is equal to 0. Matching the x term gives us minus pb plus a is equal to minus 2. And matching the constant term gives us b is equal to minus 3r. We can use these equations to find the value of p and r. The first equation gives us the value of a directly. It's 1. The second equation says that b minus pa is equal to 0. Since a is equal to 1, this simplifies to b minus p is equal to 0. Adding p to both sides tells us that b is equal to p. The third equation says that minus pb plus a is equal to minus 2. Well, we found that b is equal to p, so the pb simplifies to p squared. We also know that a is equal to 1. From here, we can solve for p. We'll subtract 1 from both sides, perform the calculation on the right, and then change the sign of both sides. This gives us p squared is equal to 3. We can get rid of the square by square rooting both sides, but we have to remember to put in a plus minus sign. Plus root 3 and minus root 3 both square to give you 3. Thankfully, we can rule out one of these answers immediately. The top of the question mentioned that p should be less than 0. So the only valid answer here is minus root 3. So we're nearly there now. The fourth equation we had was b is equal to minus 3r. Well, b is equal to p, so we can rewrite this as p is equal to minus 3r. And we know the value of p. It's minus root 3. From here, we can divide both sides by minus 3. Typing this in our calculator gives us the value of r. It's root 3 over 3. To solve question 2a, we can use the following fact. The derivative will be equal to 0 at a minimum point. We are given a minimum point, 3 minus 1. Importantly, the x value here is 3. Using our fact, we can conclude that the derivative, f dashed of x, must be equal to 0 when x is equal to 3. Well, this isn't much good to us unless we know what the derivative is, so we should start by differentiating. x squared differentiates to 2x, bx differentiates to b, and the constant c differentiates to 0. So we end up with f dashed of x is equal to 2x plus b. Now, we can use the fact that f dashed of x is equal to 0 when x is equal to 3. 2 times 3 is 6, so we end up with 0 is equal to 6 plus b. Subtracting 6 from both sides gives us that b is equal to minus 6. We are told that f of x has a minimum point at 3 minus 1. This implies that 3 minus 1 must be a point that's actually on the function. This tells us that f of x will be equal to minus 1 when x is equal to 3. We are told that f of x is equal to x squared plus bx plus c. We know that f of x must be minus 1 when x is equal to 3. We have a b appearing in this equation, and we've already found out what this is. It's minus 6. Now let's simplify. 3 squared is 9, and minus 6 times 3 is minus 18. We can clean up further on the right. 9 minus 18 is minus 9. From here, we add 9 to both sides, and then perform the calculation on the left to get our answer. C is equal to 8. Part B involves limits. There's 3 components in this expression, and we'll tackle each one individually. In the fraction n over n plus 1, I'm going to divide above and below the line by n. Above the line, we'll have n over n, which is 1. And below the line, n plus 1 all over n simplifies to 1 plus 1 over n. Next, let's look at the n plus 1000 over n term. We can split up this fraction by distributing the n beneath the line. This gives us n over n plus 1000 over n. We can simplify a bit here. N over n is equal to 1. Finally, let's look at the 1 over 3 to the power of n term. One of the laws of indices says that if you raise a fraction to a power, both the numerator and the denominator should get a copy of that power. So this can be rewritten as 1 to the power of n divided by 3 to the power of n. 1 to the power of n is 1, so this simplifies to 1 over 3 to the power of n. Now, we're ready to apply our limit. The key thing to keep in mind here is that if we have a fraction where the numerator is a constant and the denominator is going to infinity, then the limit will be equal to 0. This means that the 1 over n, the 1000 over n, and the 1 over 3 to the n will all go to 0 when we take the limit as n goes to infinity. 1 over 1 plus 0 simplifies to 1, so we end up with 1 plus 1 plus 0 plus 0, and this gives us 2. In part CI, we're asked to consider g of x minus 2. The effect of this minus 2 is that it decreases the y value by 2 in every location. In other words, we need to shift our function downwards by 2 units. This results in the blue curve I've drawn in here. In part 2, we're asked to consider g of x plus 3. Here, a shift of +3 has been applied to the input value. If we were to sub in x equal to -4, this would come out as g of -4 plus 3, which is g of -1. This means that x equal to -4 on the given function corresponds to x equal to -1 in g of x. In other words, there's been a shift of 3 units to the left. Applying this transformation to the rest of the points gives us the blue curve that I've drawn in. In part A, we must prove that √2 is not a rational number. The strategy here will be to use a proof by contradiction. We'll assume for contradiction that √2 is a rational number. Well, by definition, a rational is any number that can be written as a fraction of integers. If we assume that √2 is rational, then it can be written as a fraction p over q, where p and q are integers. Without loss of generality, we can assume that this fraction is in its simplest form. In other words, p and q have no common factors. If they did have common factors, then we could just simplify the fraction. So, we've assumed that we can write √2 equal to p over q. From here, we should do some algebra. First, I'll square both sides of the equation. Then, on the right-hand side, I'll distribute the square into the fraction. Finally, I'll multiply both sides by q squared. This brings us to an equation that 2q squared is equal to p squared. Since we assumed that p and q are integers, we know that both sides of this equation are integer valued. Because of the factor of 2, we know that 2 divides into the left-hand side of the equation. Since the left-hand side is equal to the right-hand side, 2 must also divide the right-hand side of the equation. So 2 must divide p squared. This implies that p is an even number. This comes from the fact that an odd number squared returns an odd number. So if p were odd, then p squared would be odd, and we wouldn't have 2 dividing p squared. So the only option is that p is even. Now, since p is even, it must have a factor of 2. This means that p squared will have 2 factors of 2. In other words, it must be divisible by 2 times 2 is equal to 4. So we figured out that the right-hand side, p squared, is divisible by 4. Since the left-hand side is equal to the right-hand side, the left-hand side must also be divisible by 4. In other words, we know that 4 divides 2q squared. Eliminating a factor of 2 tells us that 2 must divide q squared. And this implies that q is even. This is using a similar argument to above. If q was odd, then q squared would be odd, and we wouldn't have 2 dividing q squared. Well, we've shown that p is even, and we've shown that q is even. This means that they have a common factor of 2. But earlier, we assumed that p and q had no common factors. So we've obtained a contradiction, and this concludes our proof. In part B, we must solve an equation involving logs. There's an interesting pattern in the numbers in the bases. We have 3, 9, 27, and 81. These are all powers of 3. 9 is 3 squared, 27 is 3 cubed, and 81 is 3 to the power of 4. It'll be sensible to convert all these logs into base 3. We can do this using the formula in the hint. Applying this statement with a equal to 9, b equal to t, and c equal to 3 tells us that log base 9 of t is equal to log base 3 of t divided by log base 3 of 9. The denominator here can be typed into our calculator. When we do this, it returns a value of 2. We can do a similar thing to deal with the log base 27 of t and the log base 81 of t. Log base 27 of t will be equal to log base 3 of t divided by log base 3 of 27. Using our calculator, the denominator here evaluates to 3. Now, for the log base 81 of t, this can be written as log base 3 of t divided by log base 3 of 81. This time, the denominator evaluates to 4. We've now written each of our logs in terms of log base 3. Let's go back to the original equation and write in what we found. Now, we can factor out a common factor of log base 3 of t on the left-hand side. Next, let's divide both sides by 1 plus a half plus a third plus a quarter. Performing the calculation on the right tells us that log base 3 of t is equal to 4.8. To find the value of t, we need to get rid of the log base 3. The opposite of log base 3 is power base 3, so here we should raise both sides as a power base 3. This gives us that t is equal to 3 to the power of 4.8. To answer C part I, we must explain what log base 6 of m means. Well, log base 6 of m is the power which 6 must be raised to if you want to obtain an answer of m. Another way to think of this is that it's the value of x which satisfies the equation 6 to the x is equal to m. In other words, it's the mystery number which must be put in the power of the 6 to get out an answer of m. In the next part of the question, we're told that m is a real number which is greater than 6. We must think about log base 6 of m. Well, if you were to put a 1 in the power of a 6, you would get 6 to the 1, which is 6. We can deduce that a number less than 1 in the power will give you a value which is less than 6. A value which is greater than 1 in the power will give you a value which is greater than 6. Since we're told that m is greater than 6, the number in the power will need to be greater than 1. From here, we can conclude that log base 6 of m must be greater than 1. In part A, we must show that the complex number z1 is equal to 1 plus I is the root of a given equation. Here, 1 plus I being a root means that if we sub in z equals 1 plus I, then it will satisfy the equation. we can find the value of p by doing some algebra. To begin, I'll rewrite 1 plus I all squared as 1 plus I times 1 plus I. Now, let's multiply out some brackets. In purple, we'll have 1 times 1, which is 1, 1 times I, which is I times 1, which is I, and I times I, which is I squared. In green, we'll have 3 times 1, which is 3, 3 times I, which is plus 3I, minus 2I times 1, which is minus 2I, and minus 2I times I, which is minus 2I squared. From here, we can combine like terms. 1 plus 3 is 4. I plus 3I minus 2I comes out as plus 3I. And plus I squared minus 2I squared gives us minus I squared. By definition, I squared is equal to minus 1, so we can replace the I squared with minus 1. Now, minus 1 gives us plus 1, and 4 plus 1 gives us 5. So we end up with 5 plus 3i plus p is equal to 0. We can isolate the p if we subtract 5 and subtract 3i from both sides. This brings us to our final answer. P is equal to minus 5 minus 3i. In part B, we must use de Moivre's theorem to find the values of w for which w squared is equal to minus 1 plus root 3i. Well, de Moivre's theorem can be found in the formula book, and it states the following. R times cosine of theta plus I sine of theta, all raised to the power of n, is equal to r to the n times cosine of n theta plus I sine of n theta. This equation involves complex numbers written in polar form. However, the question hasn't provided us numbers written in this form. It will be useful to take the minus 1 plus root 3i that we were given and convert it to polar form. This can be done using your calculator. You'll end up with 2 times cosine of 120 plus I sine of 120. We can write this into the equation that we were given. Now, looking at the equation, we have a w squared on the left-hand side. We want to find the value of w, so we should get rid of the square. We can do this by square rooting both sides. However, instead of drawing in the square root symbol, instead I'll write it as a power of a half. We can do this since one of the laws of indices says that a square root is equivalent to the power of a half. We have to remember to put in a plus minus sign here, since both the positive and negative versions of a number will square to give the same answer. Now, we can apply de Moivre's theorem on the right. Here, we have r equal to 2, theta equal to 120, and n equal to a half. We can simplify here. I'll rewrite the 2 to the half as root 2. Half times 120 is 60. Turning to our calculator, cosine of 60 is a half, and sine of 60 is root 3 over 2. Next, I'll multiply in our root 2 outside the brackets. Root 2 times a half gives us root 2 over 2, and root 2 times root 3 over 2 gives us root 6 over 2. To finish, we need to deal with our plus-minus sign. So we'll split into two cases, one with a plus sign and one with a minus sign. In the first case, we simply end up with root 2 over 2 plus root 6 over 2i. In the second case, we'll get minus root 2 over 2 minus root 6 over 2i. So these are the two solutions for W. In part C, we are asked to work with an Argand diagram. A point has been plotted for us. U is equal to A plus BI. It's useful to use this point to put some labels on our axes. The real part of our number is A, and the imaginary part is B. Equipped with these labels, we can roughly mark out minus B, minus A, and B on both the real and imaginary axes. This will be very useful for when we're asked to plot complex numbers later in the question. But first, let's focus on part I. Here, we must calculate IU and IU conjugate. Well, U is equal to A plus BI. So I times U can be written as I times A plus BI. Multiplying out the brackets, I times A is AI, and I times BI is BI squared. From here, we can simplify using the fact that I squared is equal to minus 1. B times minus 1 is minus B, so we end up with AI minus B. It's conventional to write complex numbers with the real component first and the imaginary component second, so let's write this as minus B plus AI. Now, let's think about IU conjugate. Well, we've just found IU. It's minus B plus AI. To find the conjugate of a complex number, we must change the sign of the imaginary component. So here, all we have to do is change the plus AI to a minus AI. So our answer here is minus B minus AI. The next part of the question requires us to plot and label these 2 points. Well, IU has a real component of minus B and an imaginary component of A. So we go to minus B on the real axis and A on the imaginary axis and plot a point at their intersection. IU conjugate has a real component of minus B and an imaginary component of minus A. So we go to minus B on the real axis, minus A on the imaginary axis, and plot a point at their intersection. In the final part of the question, we must state a series of transformations that would send U to IU conjugate. Algebraically, 2 things have happened here. We've multiplied by I, then taken the conjugate. In terms of transformations, multiplication by I corresponds to a rotation of 90 degrees anti-clockwise. Taking a conjugate corresponds to reflecting in the horizontal real axis. Putting these two transformations in sequence gives us our answer. In part A, we must differentiate the function f of x is equal to 1 over 5x squared plus 7. This expression is a fraction. The quotient rule can be used to differentiate fractions. This states that u over v differentiates to v du dx minus u dv dx, all divided by v squared. Here, u refers to the number above the line. In our situation, u is equal to 1. V is the expression below the line. We'll have v equal to 5x squared plus 7. To apply the quotient rule, we'll need to differentiate both of these expressions. The constant 1 will simply differentiate to 0, so du dx is equal to 0. To differentiate 5x squared, we use the rule of multiplying down by the power, then reducing the power by 1. So 5x squared differentiates to 10x. The plus 7 is a constant, and this will differentiate to 0. So dv dx is equal to 10x. From here, we simply have to sub in these expressions into the quotient rule. To finish, we can simplify the numerator. Anything by 0 gives you 0, and minus 1 times 10x is minus 10x. In part B, we're given a function g of x and asked to find g dashed of pi over 2. To do this, we must first find the derivative g dashed of x and then sub in pi over 2. G of x is equal to tan of x over 2 multiplied by ln of x. The high-level structure here is that we're multiplying together two expressions. The product rule can be used in this scenario. This states that u times v differentiates to u dv dx plus v du dx. In this question, we can label the tan x over 2 as u and the ln of x as v. To apply the product rule, we'll need to differentiate both of these expressions. The ln of x is quite straightforward. There's a rule in our tables which says that ln of x differentiates to 1 over x. So dv dx is 1 over x. When it comes to the tan x over 2, things are a bit more tricky. Here, we'll need to use a chain rule. This involves performing two differentiations, an inner differentiation and an outer differentiation. On the inside of the tan, we have an x over 2. This can be rewritten as a half times x. If we differentiate this, it comes out as a half. On the outer level, our expression looks like tan of something. There's a rule in our tables which says that tan of x differentiates to secant squared of x. Using this pattern, tan of something will differentiate to secant squared of that something. In this scenario, we have an x over 2 in the place of the question mark, so we end up with secant squared of x over 2. We've performed our inner differentiation and our outer differentiation. To get the overall derivative, we multiply these two expressions together. So we'll have a half multiplied by secant squared of x over 2. So this is the value of du dx. Now that we know the values of u, v, du dx and dv dx, we can find the derivative g dashed of x by subbing in to the product rule statement. We were asked to find g dashed of pi over 2. To find this, we should sub in x equal to pi over 2 into this expression. From here, we can simplify a bit. Pi over 2 divided by 2 gives us pi over 4. 1 divided by pi over 2 gives us 2 over pi. And again, pi over 2 divided by 2 gives us pi over 4. Now, we can turn to our calculator to evaluate tan of pi over 4. And it's crucial that we're in radians mode here. This comes out as 1. By definition, secant of x is equal to 1 over cosine of x. So secant squared of pi over 4 will be 1 over cosine squared of pi over 4. This can be rewritten as 1 over cosine of pi over 4 all squared. If we type this into our calculator, we'll get an answer of 2. Now, for the final simplifications, 1 times 2 over pi is 2 over pi. A half times 2 is 1, so we end up with ln of pi over 2 times 1, which is ln of pi over 2. In part C, we're given 3 sets, a, b and c. F is a function which maps from a to b, and g is a function which maps from b to c. The first task is to find the value of g of f of 3. To begin, we should find f of 3. Well, 3 appears here. When we apply f, we get mapped to the icon of the world. When we apply g to this icon, we end up at w. So g of f of 3 is equal to g of the icon of the world, which is w. In part 2, we must explain why g is injective but not surjective. Well, by definition, a function is not injective if 2 inputs map to the same output. Another way to think of this is that it is injective if no output value has more than one arrow coming into it. If we look at the output values, x, w, y and z, none of these have more than one arrow coming in. So this means that g is injective. A function is surjective if every single output value has an arrow coming into it. This means that it's not surjective if we can find an output value with no arrow. Well, looking at the output set C, we see that y has no arrow coming into it. So the function g is not surjective. In part A, we're presented with 2 functions, f of x and g of x. The first task is to find 2 values of x for which these functions are equal. Our starting point is the equation f of x is equal to g of x. Well, f of x is x plus 4 and g of x is x squared minus 2, so let's write these in. Now, I'll group everything on the right hand side by subtracting x and subtracting 4 from both sides. We can simplify on the right. minus 2 minus 4 is equal to minus 6. We now have a quadratic expression on the right-hand side. This can be factorized. To do this, we need to pick a pair of numbers which multiply to minus 6 and add to minus 1. Here, minus 3 and plus 2 do the job. So our factorization is x minus 3 times x plus 2. We know that these two factors must multiply together to give 0. The only way that this can happen is if one of the factors is 0 itself. So either x minus 3 is equal to 0, or x plus 2 is equal to 0. Both of these cases are straightforward to solve. If x minus 3 is 0, we can add 3 to both sides to get x is equal to 3. If x plus 2 was equal to 0, we can subtract 2 from both sides to get x is equal to minus 2. In part 2, we must find the area between the two functions in the range x is minus 1 to x is plus 2. An important thing to observe here is that f is always greater than g in the specified range. This means that we can find the area by calculating a definite integral of f of x minus g of x. The limits will be the specified x values, minus 1 and 2. Well, by definition, f of x is equal to x plus 4, and g of x is equal to x squared minus 2. Now, distributing the minus sign gives us minus x squared and minus minus 2, which is plus 2. Next, we can combine the constant terms. Plus 4 plus 2 is 6. We're now ready to integrate. A useful thing to remember here is the rule for integrating powers of x. Raise the power by 1 and then divide by the new power. Looking at the x, we can think of this as x to the 1. This will integrate to x squared over 2. Minus x squared will integrate to minus x cubed over 3. A constant term will always integrate to that constant times x. So 6 integrates to 6x. We needed to calculate the definite integral from minus 1 to 2. To calculate this, we sub in the upper limit, x equal to 2, and sub in the lower limit, x equal to minus 1, and subtract away the answers. From here, all we have to do is some calculator work. When we sub in the upper limit, it comes out as 34 over 3. When we sub in the lower limit, it comes out as minus 31 over 6. To obtain our final answer, we simply need to calculate 34 over 3 minus 31 over 6. This comes out as 33 over 2 square units. In part B, we're given an equation involving an integral. The equation involves a constant b, and we need to find out what this is. To get started, let's focus on the integral on the left-hand side of the equation. We'll ignore the limits for now and just focus on the integration. Multiplicative constants can be brought outside the integral sign. Here, b is a constant which is being multiplied by the e to the bx. This means that we can bring the b outside the integral sign. There's a rule in the formula book which says that e to the ax integrates to 1 over a times e to the ax. We can apply that statement here with b in the place of a. Now, the b and the 1 over b will cancel, so we end up with e to the bx. The equation we're given has the definite integral from 0 to b. To deal with this, we'll take the answer of the integral, e to the bx, sub in the upper limit, b, and sub in the lower limit, 0, and subtract these answers away. b times b is b squared, and b times 0 is 0. Then, e to the 0 simplifies to 1. You can find this by typing e to the 0 in your calculator, or by using the fact that anything to the power of 0 gives you 1. So, we've managed to calculate the integral on the left-hand side of the equation. Let's write in what we found. From here, we need to do some algebra to solve for b. To begin, I'll add 1 to both sides. The inverse of a power base e is a logarithm base e. So the next step is to take log base e of both sides. ln is shorthand notation for log base e. Next, we'll need to get rid of the square. The inverse of a square is a square root. So here, let's square root both sides. We have to be careful and write in a plus-minus sign here. This is because the positive and negative versions of a number both square to give you the same answer. However, we don't want both of these solutions. At the top of the question, we were told that b is a positive constant. So we only want b is equal to plus the square root of ln of e plus 1. If you like, you can type this expression into your calculator to get it in decimal form. It'll come out as approximately 1.146. In question 7, we are given a function, v of t, which specifies Fiona's speed t minutes after passing a specific point, A, on a motorway. In part A, we need to find out Fiona's speed when she passes the point A. Well, t represents the time in minutes after passing the point A. At the instant she passes A, 0 minutes will have passed. So all we need to do is sub in t equal to 0 into our function. When we do this, we get out an answer of 109 kilometers per hour. In part B, we must work out Fiona's acceleration 5 minutes after passing the point A. Acceleration can be thought of as the rate of change of your speed. Differentiating a function allows us to find the rate of change. This means that the acceleration is found by differentiating the speed function that we were given. To differentiate 2 over 3t cubed, we can use the rule for differentiating powers. Multiply down by the power and then reduce the power by 1. This gives us 2t squared. The same rule can be applied for the minus 6t squared. We multiply down by the power, then reduce the power by 1. This gives us minus 12t. A constant times t simply differentiates to the constant, so 13t will differentiate to 13. Additive constants differentiate to 0, so the plus 109 will differentiate to 0 and simply disappear. This means that the acceleration function v dashed of t is equal to 2t squared minus 12t plus 13. We want to find the acceleration 5 minutes after passing the point A. So we should sub in t equal to 5 into the acceleration function. When we perform the resulting calculation, we end up with an answer of 3 kilometers per hour per minute. In part C, we must find the time at which Fiona reaches her maximum speed during the first 4 minutes. Well, there's an important fact in differentiation which says that minimum and maximum points occur when the derivative is equal to 0. So if we want a maximum of the speed function v of t, we should set the derivative v dashed of t equal to 0. Thankfully, we found this function in part B. V dash of t was equal to 2t squared minus 12t plus 13. We end up with a quadratic equation. This can be solved using the quadratic formula. T will be equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. Here, a refers to the number in front of the t squared, so a is 2. B is the number in front of the t, so b will be minus 12. And c is the constant by itself, so c will be plus 13. Let's sub these values into our formula. From here we can simplify. Minus 12 is plus 12. The expression under the square root evaluates to 40. And beneath the line we have 2 times 2, which is equal to 4. To deal with the plus minus sign, we need to split into 2 cases. In the first, we replace this symbol with a plus, and in the second, we replace it with a minus. Both of these fractions can be evaluated using our calculator. In the first case, we end up with 4.58, and in the second case, we end up with 1.42. So these are the 2 time values where the derivative v dashed of t is equal to 0. We were asked for a time that occurred during the first 4 minutes. This rules out the 4.58, so we're left with a final answer of t equal to 1.42. If you wanted, you could prove that this was indeed a maximum point by showing that the second derivative is negative at this value. V double dashed of t comes out as 4t minus 12. When you sub 1.42 into this function, you end up with minus 6.32. In part D, we must use integration to work out Fiona's average speed over the first 5 minutes. To find this, we'll calculate the definite integral from 0 to 5 of the speed function v of t. Then, we'll divide this by the length of the interval. In other words, we'll multiply it by 1 over 5 minus 0. 5 minus 0 is equal to 5, and we can write in the expression for v of t from the previous page. Now it's time to integrate. The main rule we'll apply here is for integrating powers. Raise the power by 1, then divide by the new power. Focusing on the 2 over 3 t to the power of 3, We'll raise the power from 3 to 4 and then divide by 4. This gives us 2 over 12 times t to the 4. For the minus 6t squared, we raise the power from 2 to 3 and then divide by 3. So we end up with minus 6t cubed over 3. 13t is the same as 13t to the power of 1. So to integrate this, we'll raise the power from 1 to 2 and then divide by 2. This gives us 13t squared over 2. A constant will integrate to that constant times t. So 109 integrates to 109t. We wanted the definite integral between 0 and 5. To find this, we need to sub in the upper limit, 5, and sub in the lower limit, 0, and subtract away the answers. When we perform the calculator work, the upper limit evaluates to 561.6667. The lower limit evaluates to 0. When we multiply this by the 1 over 5 in front of the brackets, we end up with 112.3333. The question wants us to round to 2 decimal places, so our final answer is 12.33 kilometers per hour. In part E, we are provided with some information. V dashed of 1 is greater than 0, and V double dashed of 1 is less than 0. We are presented with 4 graphs, and we must determine which of these V of t must look like. The derivative V dashed represents the rate of change of V. Since V dashed of 1 is greater than 0, this means that we have a positive rate of change. In other words, V of t is increasing at t equal to 1. Since graphs A and C are decreasing at t equal to 1, we can rule these out. The second derivative, V double dashed, represents the rate of change of V dashed. Since V double dashed of 1 is less than 0, this means that the rate of change, V dashed of t, is decreasing. In other words, the rate of ascent is getting smaller. The function is increasing, but it's starting to level out. B is the only graph with this property, so our final answer here is graph B. In part F, we're told that there's 2 points on the motorway, A and B, which are 10 kilometers apart. We need to find the minimum time in minutes that a driver could get from A to B while never driving above 100 kilometers per hour. Well, the larger the speed is, the shorter the journey will take. So if we want to minimize the time, it makes sense to maximize the speed. Our speed is never allowed to go above 100 kilometers per hour. However, we can travel at exactly 100 kilometers per hour for the duration of the journey. To find our time, we can use the distance, speed, time triangle. Since we want to find the time, we should block out this portion of the triangle and look at the 2 quantities which remain. Here we have distance over speed. We're travelling between point A and point B, and the distance between these is 10 kilometers. Our speed is 100 kilometers per hour. So we end up with 10 over 100, which is 0.1. Since the speed was in kilometers per hour, the unit here is hours. However, the question wants the answer in minutes. To convert from hours to minutes, we simply multiply by 60. This brings us to our final answer of 6 minutes. In part G, we're told that Rowan drives from point A to point B. He travels at a constant speed of 120 kilometers per hour for the first 2 minutes. Then he starts to decelerate. And we're told that his average speed in driving from point A to point B is 100 kilometers per hour. We need to use this to figure out his deceleration. To start, let's think about the first 2 minutes of his journey. Since our speeds are given in kilometers per hour, I'll convert this to hours. 2 minutes will be 2 over 60 hours. During the first 2 minutes, Rowan has a constant speed of 120 kilometers per hour. To find the distance covered here, we multiply his speed by the time. This gives us 120 times 2 over 60, which comes out as 4 kilometers. So, we know that in the first 2 minutes of his journey, he travelled 4 kilometers. In the previous part of the question, we showed that if you travelled from A to B at a constant speed of 100 kilometers per hour, the journey would take 6 minutes. Since Rowan has an average speed of 100 kilometers per hour, it follows that his journey must also take 6 minutes. So, all in all, we know that Rowan travels 10 kilometers in 6 minutes. We've already shown that 4 kilometers were covered in the first 2 minutes. 10 minus 4 is 6, so there's 6 kilometers left over. 6 minus 2 is 4, so there's 4 minutes left over. This means that after deceleration starts, Rowan will travel 6 kilometers in 4 minutes. If we multiply both sides by 15, this corresponds to an average speed of 90 kilometers in 1 hour. I've performed this conversion since all our speeds are listed in kilometers per hour. Well, focusing on this blue deceleration period, Rowan starts at a speed of 120 kilometers per hour. Over the whole period, we know that he has an average of 90 kilometers per hour. Since his deceleration is constant, the average speed will be exactly halfway between the starting speed and the ending speed. It follows that he must end with a speed of 60 kilometers per hour. So, over the 4 minutes of deceleration, Rowan's speed has changed from 120 to 60. This represents a decrease of 60 kilometers per hour. To find the deceleration per minute, we should divide 60 by 4. This brings us to our final answer of 15 kilometers per hour per minute. In part A, we're told that Olga puts in €3,000 to a savings account. Interest is added at an annual rate of 2.4% per year, and we need to find the amount of money in the account after 5 years. To solve this question, we should open up our formula book and grab the result for compound interest. This states that f is equal to p times 1 plus I to the power of t. Here, F represents the final value, and that's what we're trying to find in this question. P represents the start amount, and here we're starting with €3,000. I is equal to the interest rate, and in our question, this is 2.4%. Written as a decimal, this is 0.024. T represents the time period, and since our money is invested for 5 years, we will have T equal to 5. Let's sub these values into our formula. We can type the right-hand side into our calculator and then round to the nearest cent. This gives us a final answer of €3,377.70. In the next part of the question, we must explain what is meant by the present value of a payment of €1,000 in 1 year's time at a particular interest rate. Well, in general, a present value represents the amount of money you would need to invest right now in the present moment to obtain the specified value in the future. So the answer here is it's the amount of money you would need to invest right now to end up with €1,000 in 1 year's time after adding any interest you might earn. In part BII, we're told that Chen invests money in a savings account with the same interest rate of 2.4% per year. We know that after 6 years, he'll end up with €4,000 in the account, and we need to figure out how much money he put in originally. To solve this, we'll turn to our compound interest formula once again. F is equal to P times 1 plus I all to the power of T. F represents the final value, and we know that Chen ends up with €4,000, so F is equal to 4,000. P represents the start amount, and this is the quantity we're trying to find. I is the interest rate, which is 2.4%. Written as a decimal, this is 0.024. T represents the time period, and since Chen's money is invested for 6 years, we'll have T equal to 6. Let's go ahead and sub these values into the formula. We want to find the value of P, but it's being multiplied by an expression. To isolate P, we should divide both sides by this expression. We can type the left-hand side into our calculator, and when we round to the nearest cent, we end up with a final answer of €3,469.45. In part C, Fiona is taking out a loan with an interest rate of 2.4% per year. She makes payments quarterly, and we need to figure out the quarterly interest rate, which would be equivalent to the APR of 2.4%. Well, an annual rate of 2.4% means that in 1 year, €100 would grow to €102.40. We want to work with quarters, and there's 4 quarters in a year. So a good starting point is the following. After 4 compounding periods, €100 would grow to €102.40. We can put this information into the compound interest formula. F is equal to P times 1 plus I to the power of T. Here, F, the final value, is 102.40. P, the starting value, is 100, and t, the time period, is 4. I, the quarterly interest rate, is the unknown that we're trying to find. If we do a bit of algebra, we can find out what I is. To begin, I'll divide both sides by 100. Then, we can simplify the left-hand side using our calculator. To get rid of the power of 4, we should take the 4th root of both sides. Now, to get rid of the plus 1, we should subtract 1 from both sides. Typing the left-hand side into our calculator tells us that I is equal to 0.005947. We want our answer in percentage form. To convert this decimal to a percentage, we multiply by 100. Rounding to 2 decimal places, we get our final answer that I, the quarterly interest rate, is 0.59%. In Part D, Rowan deposits money into a savings account at the start of each month for 36 months. We know that at the end of this 3-year period, Rowan will have €12,000 in the account. We also know that interest is calculated at a rate of 0.11% per month. In Part I, we assume that Rowan deposits €A at the start of each month, and we must write down a geometric series to capture the total amount of money at the end of the 3 years. Our good old friend, the compound interest formula, will help us here. The monthly interest rate is 0.11%. Written as a decimal, this is 0.0011. This means that if we invest a starting value of €A for a time period of m months, the amount of money it will yield is A times 1 plus 0.0011 to the power of m. Performing the addition in the brackets, this simplifies to A times 1.0011 to the m. The first payment that Rowan puts into the savings account gets invested for the full 36-month period. So at the end, its value will be A times 1.0011 to the power of 36. The second payment, which he makes at the beginning of the second month, will only be invested for 35 months. So its value at the end will be A times 1.0011 to the power of 35. This pattern continues. The third payment will be invested for 34 months, so the power there would be 34. The fourth payment is invested for 33 months, so the power there would be 33. If we continue this pattern all the way down, the second last payment that is made will only be invested for 2 months. The value here will be A times 1.0011 to the power of 2. The last payment is made at the beginning of the final month, so it's only invested for 1 month. The value here will be A times 1.0011 to the power of 1. To find the total amount in the account at the end of the 36 months, we simply add together the yields for each of our 36 payments. In the next part of the question, we must find the value of A, which will give a total amount of €12,000 after the 3 years. To get started, we'll take the equation we found in the previous part of the question and replace the total amount with a target of €12,000. From here, we can factor out the common factor of A on the right-hand side. Next, I'll reorder the sum inside the square brackets. Instead of writing our powers in decreasing order from 36 down to 1, instead I'll write them in increasing order from 1 up to 36. The reason that I'm doing this is because it'll make it easier to apply the sum of a geometric series formula. This result can be found in the formula book, and it says that S of n, the sum of the first n terms of a geometric series, is a times 1 minus r to the n divided by 1 minus r. In this formula, a refers to the first term. In our series, that's 1.0011 to the power of 1, which can be simplified to 1.0011. R is the common ratio, and this represents the expression we must multiply by to get from one term of our sequence to the next. In our sequence, the powers are increasing by 1 for each successive term. Since powers represent repeated multiplication, one way to view this is that each time we're moving from one term to the next, we're multiplying by another copy of 1.0011. This means that the common ratio R is 1.0011. N represents the number of terms in the sequence. Well, we start with a power of 1 and end with a power of 36. It follows that the total number of terms in the sequence, n, is equal to 36. We can turn to our calculator to find this fraction. It comes out as 36.74209. So this is the value that the sum inside of the square brackets comes out as. We're getting close now. We have the a on the right-hand side of the equation, but it's being multiplied by a number. To get rid of this, we should divide both sides by that number. Performing the calculation on the left and rounding to the nearest cent gives us a final answer that a is equal to €326.60. In Part E, we're given information about 3 types of tickets sold by a park. A child ticket costs €11 and makes up 52% of ticket sales. A student ticket costs €5 less than an adult ticket and consists of 15% of ticket sales. An adult ticket costs X euro and makes up 33% of sales. We know that the expected value of a ticket price is €13.85. We must use this information to find out the value of X. Well, an adult ticket costs X euro and a student ticket costs €5 less than this. This means that a student ticket will cost X minus €5. To find an expected value, we must multiply together each value with its corresponding probability. Here, we'll get 11 times 52%, X minus 5 times 15%, and X times 33%. The expected value is found by adding these 3 terms together. In this question, we're told that the expected value is 13.85. To make things easier for our calculator, I'll convert these percentages into decimal form. We do this by dividing by 100 and removing the percentage sign. 52% is equal to 0.52, 15% is 0.15, and 33% is 0.33. Now let's simplify. Using our calculator, 11 times 0.52 is 5.72. Multiplying out our brackets, x times 0.15 is 0.15x, and minus 5 times 0.15 comes out as minus 0.75. X times 0.33 can be rewritten as 0.33x. From here, we can combine the number terms and the x terms on the right-hand side. 5.72 minus 0.75 comes out as 4.97. 0.15x plus 0.33x comes out as 0.48x. Now, I'll subtract 4.97 from both sides, and then perform the calculation on the left. From here, we divide both sides by 0.48, and then we use our calculator to compute the fraction on the left-hand side. This brings us to our final answer, that x is equal to 18.5 euro. In part F, we're provided with some definitions. The markup is the profit as a percentage of the cost price. The margin is the profit as a percentage of the selling price. We know that a shop sells an item with a margin of 18%, and we need to find the markup. Things are quite abstract here, and it'll be beneficial to ground things with a concrete example. 100 is a nice round number which is easy to work with. So let's make the assumption that the selling price was 100 euro. The margin is the profit as a percentage of the selling price. If the selling price is 100 euro, then a margin of 18% simply corresponds to a profit of 18 euro. We need to find the markup, and this involves the cost price. This can be found by taking the selling price and subtracting the profit. This gives us 100 euro minus 18 euro, which is 82 euro. To find the markup, all we have to do is divide the profit by the cost price. This gives us 18 over 82, which comes out as 0.21951. The markup should be written as a percentage. To convert this from decimal to percentage form, we multiply by 100 and write in the percentage sign. When we round off to the nearest percent, we get the final answer that the markup is equal to 22%. In question 9, we must investigate the factors of different numbers. The first task is to list the 5 different factors of 2 to the power of 4. Well, using our calculator, 2 to the power of 4 is equal to 16. The factors will be the numbers which divide evenly into 16. With a little bit of thought, we can list these out. The factors are 1, 2, 4, 8, and 16. There's a very nice pattern here when you write these factors as a power base 2. 1 is 2 to the power of 0, 2 is 2 to the power of 1, 4 is 2 to the power of 2, 8 is 2 to the power of 3, and 16 is 2 to the power of 4. So, to find all the factors of 2 to the power of 4, all we have to do is write all the numbers from 0 to 4 in the power of a 2. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and 2 to the 4. This pattern is very helpful when it comes to part 2 of the question. Here, we need to work out how many factors 3 to the 7 has. Here, all we have to do is write all the numbers from 0 to 7 in the power of a 3. The factors are 3 to the 0, 3 to the 1, 3 to the 2, 3 to the 3, 3 to the 4, 3 to the 5, 3 to the 6, and 3 to the 7. There's 8 numbers on this list, so 3 to the 7 has 8 factors. In part 3, we must work out how many factors 2 to the 10 times 3 to the 12 has. To solve this, we'll need to generalize the idea from above. The factors of 2 to the 10 can all be written in the form 2 to the a, where a is a whole number between 0 and 10. The factors of 3 to the 12 can all be written in the form 3 to the b, where b is a whole number between 0 and 12. To find the number of factors for 2 to the 10 times 3 to the 12, we'll have to consider all the different combinations of these. In other words, the factors will be of the form 2 to the a times 3 to the b. For example, 2 to the 4 times 3 to the 2, 2 to the 7 times 3 to the 0, or 2 to the 1 times 3 to the 9. So there's 3 examples, but there's many, many more. To find the total number of factors, we'll have to figure out how many there are. Well, a, the number that's in the power of the 2, must be a whole number between 0 and 10. So there's 11 choices for a. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. B, the number in the power of the 3, must be a whole number between 0 and 12. There's 13 choices here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. To find the total number of ways to pair a choice with A with a choice for B, we should multiply together the 11 by the 13. This gives us our final answer of 143 ways to form a factor of 2 to the 10 times 3 to the 12. In part B, we're looking at pairs of factors of 12. In other words, that's pairs of natural numbers, x and y, such that x multiplied by y gives you 12. The first task is to complete a table showing these pairs. The key to doing this is the following. Whatever numbers we write in, each column must multiply together to give you 12. This means that if we have a column with one number written in, the other number must be 12 divided by that number. The y value in the first column will be 12 divided by 1, which is 12. The y value in the second column will be 12 divided by 2, which is 6. The y value in the second last column will be 12 divided by 6, which is 2. and the x value in the final column will be 12 divided by 1, which is 12. There was one column in the middle which had neither box filled in. Each of the rows should contain all the factors of 12. If you look through the x row, you'll notice that 4 is the missing factor, so that's what we should write in. To find the corresponding y value, we divide 12 by 4 and get 3. In the next part of the question, we must plot these 6 points on a coordinate diagram. The first point has an x value of 1 and a y value of 12. So we go to 1 on the x-axis, 12 on the y-axis, and plot a point at their intersection. The next point has an x value of 2 and a y value of 6. The next point, 3, 4, is already plotted for us. After this, we've an x value of 4 and a y value of 3. Next is an x of 6 and a y of 2. And finally, we have an x of 12 and a y of 1. This gives us 6 points plotted on the diagram. In part 3, we're told that the relationship between x and y is that y is equal to 12 over x. We need to draw the graph of this function above. Well, we've already drawn in 6 reference points. To draw the graph, all we have to do is join these points with a nice smooth curve. In part C, we are told that a tangent to the curve y equals 12 over x is drawn at the point p, 12 over p. We must show that the equation of the tangent line is equal to a given expression. If we look through the formula book, we'll find a result for the equation of a line. Y minus y1 is equal to m times x minus x1. To use this formula, we need to know 2 things: a point on the line and the slope of the line. We are given the point directly. It's p 12 over p. This gives us the x1 and the y1 values for the formula. Finding the slope m is a bit more tricky. To do this, we'll use the fact that the derivative dy dx represents the slope. It'll be a good idea to find what this derivative is. The function is y equal to 12 over x. We can think of this as 12 over x to the power of 1, and then use the law of indices, which says we can move a power from below the line to above the line as long as we change the sign. This gives us 12x to the minus 1. We can find the derivative dy dx by differentiating this expression. We'll want to use our rule for differentiating powers of x. Multiply down by the power, then reduce the power by 1. Here, the power is minus 1, so we multiply down by minus 1, and then we reduce it from minus 1 to minus 2. This gives us minus 12 x to the minus 2. Using our laws of indices, this can be rewritten as minus 12 over x to the plus 2. We want to find the slope at the point p 12 over p. The x value here is p, so to find our slope, we should sub in x equal to p into our derivative. This gives us minus 12 over p squared. We're now ready to sub in to the equation of a line formula. x1 is equal to p, y1 is equal to 12 over p, and m is equal to minus 12 over p squared. In the target expression we were given, y is all by itself on the left-hand side of the equation. We should do some algebra to get our equation into this form. To start, let's multiply out the brackets on the right. Minus 12 over p squared times x gives us minus 12 over p squared x. Minus 12 over p squared times minus p gives us minus 12p over p squared. The two minus signs here combine to give us a plus, and we can cancel the p above the line with one of the p's below the line. Now, we can remove the minus 12 over p from the left-hand side by adding 12p to both sides. If we want to add together fractions with the same denominators, we simply add the numerators. So 12 over p plus 12 over p comes out as 24 over p. As our final answer, we end up with y equal to minus 12 over p squared times x plus 24 over p. This is precisely the expression we were asked to obtain. In C part 2, we are told that the area of the triangle formed by the x-axis, the y-axis, and the tangent line always comes out as k square units. We need to figure out the value of k. We've been provided with a nice diagram. The question essentially boils down to figuring out the area of the grey triangle. There's a formula which says that the area of the triangle is half times the base times the perpendicular height. This means if we can find the base and perpendicular height, the area will follow. Looking at our diagram, the base of the triangle corresponds to the x-intercept of the line. The perpendicular height corresponds to the y-intercept. Let's go ahead and find what these intercepts are. To find the x-intercept, we should let y equal to 0 in our equation. From here, we can do some algebra to solve for x. I'll begin by subtracting 24 over p from both sides. The fraction minus 12 over p squared is a bit awkward. We can get rid of this fraction by multiplying both sides by its denominator, p squared. On the left, p squared divided by p leaves us with p. On the right, the multiplication by p squared cancels off the division by p squared. This brings us to minus 24p is equal to minus 12x. As our final step, we can remove the multiplication by minus 12 by dividing both sides by minus 12. Since minus 24 divided by minus 12 is 2, we end up with x equal to 2p. So that's the value of our x-intercept. To find the y-intercept, we should let x equal to 0 in our equation. Minus 12 over p squared times 0 simply comes out as 0, so we're left with y equal to 24 over p. So, the area of the triangle will be half times the base times the perpendicular height. The base was equal to our x-intercept, and we found that this was 2p. The perpendicular height corresponded to the y-intercept, and we found that this was 24 over p. So, we get a half times 2p times 24 over p. The multiplication by p and the division by p will cancel, so we end up with a half times 2 times 24. Performing this calculation gives us our final answer of 24 square units. In question 10, we're presented with a triangle. It has a base of 2 and a perpendicular height of 8. We are provided the first 3 terms of a sequence based on this triangle. The first term contains 1 rectangle. The second term contains 2 rectangles which are of equal height. The third term contains 3 rectangles of equal height. In part A, we must draw the fourth pattern. Well, the fourth pattern will contain 4 rectangles of equal height. The triangle has a perpendicular height of 8 units. If we split this evenly across 4 rectangles, then each one will have a height of 2 units. To draw the pattern, we should start by drawing horizontal lines through the triangle. We start by drawing a line along the base. Then we move up 2 units and draw a line. From here, we move up another 2 units and draw a line. And finally, we move another 2 units and draw a line. These 4 lines represent the bottom side of each of the 4 rectangles. To finish the pattern, we simply need to draw in the other 3 sides of each rectangle. In part B, we must show that the total area of the 3 rectangles in T3 is 32 over 3 square units. To tackle this question, we should try to find the area of each rectangle individually. To do this, we should try to find the height and the width of each rectangle. The total height of the triangle is 8 units. Since this is split equally among the 3 rectangles, each rectangle will have a height of 8 over 3 units. At the bottom of the triangle, we have a width of 2. At the top of the triangle, we simply have a point. So here, the width is 0. So essentially, the width grows from 0 units at the top of the triangle up to 2 units at the base. Since the sides of the triangle are straight lines, as we move down from top to bottom, the width will be increasing at a steady rate. The total increase in width is 2 units, and this happens over the duration of 3 rectangles. This means that the growth per rectangle will be 2 over 3 units. We can illustrate this in our diagram. At the top of the triangle, we have a width of 0. When we reach the bottom of the first rectangle, this will have grown by 2 over 3. By the time we reach the bottom of the second rectangle, the width will grow by another 2 over 3. This gives us a width of 4 over 3. By the time we reach the base of the third triangle, the width will again increase by 2 over 3. So here, the width is 4 over 3 plus 2 over 3, which is 2. Now that we know the heights and widths of each rectangle, we can find their areas by multiplying them together. The area of the top rectangle will be 8 over 3 times 2 over 3. This comes out as 16 over 9. The area of the middle rectangle will be 8 over 3 times 4 over 3, and this comes out as 32 over 9. The area of the bottom triangle will be 8 over 3 times 2. This comes out as 16 over 3. To find the total area of the 3 rectangles, all we have to do is add these 3 results together. This gives us an answer of 32 over 3 square units. This is precisely the answer that we wanted to obtain. In part C, we must find the total area of the n rectangles in T of n. In part B, we found the total area of the 3 rectangles in T of 3. To solve this question, we simply need to generalize the strategy we used for part B. The total height of the triangle is 8 units. In Tn, we're going to split this equally among n rectangles. This means that each rectangle will have a height of 8 over n units. The width of the triangle grows from 0 units at the top to 2 units at the base. Since the width will increase at a steady rate, the growth over each of the n rectangles will be the same. Starting at the top of the triangle and moving our way down, each successive rectangle will have a width that's 2 over n greater than the previous rectangle. The top rectangle will have a width of 2 over n. The second rectangle will have a width of 4 over n. The third rectangle has a width of 6 over n, and so on. The second rectangle from the bottom will have a width of 2n minus 2 over n, and the bottom rectangle will have a width of 2n over n. We could simplify this to 2, but it's actually more convenient to leave it as 2n over n. So, we know that the height of each rectangle is 8 over n, and we have a list of all the rectangle widths. To find the area of each individual rectangle, we simply multiply together the height by the width. The highest rectangle will have an area of 8 over n times 2 over n. The second rectangle has an area of 8 over n times 4 over n. This pattern continues all the way down to the bottommost rectangle, which will have an area of 8 over n times 2n over n. To find the total area of all the rectangles, we simply need to add up all the individual areas. There's a common factor of 8 over n here, so let's factor this out. If we focus inside the square brackets, each of the fractions has an n in the denominator. This means that 1 over n is a common factor for each of these terms. We can also factor this out. We are left with the sum of an arithmetic sequence inside the square brackets. There's a result in the formula book which will help us find this. It says that Sn the sum of the first n terms in an arithmetic sequence is n over 2 times 2a plus n minus 1 times d. In this formula, n refers to the number of terms in your sequence. Well, in our sequence, we were adding together the areas of n different rectangles, so the sum will contain n terms. This means that the n in the formula is simply equal to n. A refers to the first term, and in our sequence this is 2. D is the common difference, and this represents the jump that's needed to get from one term to the next term in your sequence. In our sequence, the numbers are increasing by 2 each time, so D is equal to 2. We can simplify a bit here. 2 times 2 is 4, and multiplying out the brackets, n by 2 is 2n, and minus 1 by 2 is minus 2. We can clean things up a bit by combining things into a single fraction. The n will appear above the line, and the 2 will appear below the line. I've also simplified the 4 minus 2 to 2. So, we found the sum of the terms in the square brackets. It's n times 2 plus 2n all over 2. Now we can simplify. The n above the line will cancel with one of the n's below the line. And 2 divides into 8 4 times. To finish off, we can multiply out the brackets in the numerator. 4 times 2 is 8, and 4 times 2n is 8n. So our final answer is 8 plus 8n over n square units. In part D, we're told that the total area of a different sequence of rectangles is an is equal to 8 times n minus 1 over n. We must find the first value of n for which an is greater than 95% of the area of the triangle. Well, there's a formula which says the area of a triangle is a half times the base times the perpendicular height. Our triangle has a base of 2 and a perpendicular height of 8. So the area is a half times 2 times 8, which comes out as 8 square units. 95% of this area would be 8 times 95%, which is 7.6. We want to have an greater than 95% of the area, which means that we'll need an greater than 7.6. When we write in the given expression for an, we end up with the following inequality. 8 times n minus 1 over n is greater than 7.6. We can solve this inequality to find the value of n. To begin, I'll multiply both sides by n. Then, I'll multiply out the brackets on the left. 8 times n is 8n, and 8 times minus 1 is minus 8. Next, I'll group the n terms on the left-hand side by subtracting 7.6n from both sides. We can simplify on the left. 8n minus 7.6n is 0.4n. From here, we can remove the multiplication of 0.4 by dividing both sides by 0.4. After we perform the calculation on the right, we end up with n is greater than 20. Since n is a whole number, the smallest value of n which satisfies this would be n equal to 21. And that's our final answer. In part E, we're presented with two diagrams. In diagram A, we have a square-based pyramid. The side length of the square in the base is c. The perpendicular height of the pyramid is h. In diagram B, we have the same pyramid, but this time we have a horizontal slice taken x units from the top. We're given a formula to find the area of the shaded section. S of x is equal to x squared c squared over h squared. In part I, we are given an expression for the volume of the pyramid and then asked to find this volume. The expression we're given is the definite integral from 0 to h of s of x dx. Well, we're told what s of x is. It's x squared c squared over h squared. So let's write this in. Because of the presence of the dx, we are integrating with respect to x. This means that c and h can both be treated like constants. Multiplicative constants can be brought outside the integral sign, so we can bring out the c squared over h squared. Now we can integrate. The rule for integrating powers of x is to raise the power by 1 and then divide by the new power. We have x to the power of 2, so we raise the power from 2 to 3 and then divide by 3. Since we had the definite integral from 0 to h, we should sub in the upper limit, x equal to h, and sub in the lower limit, x equal to 0, and subtract away the two answers. 0 cubed over 3 simply comes out as 0, so the expression inside the square brackets simplifies to h cubed over 3. H cubed divided by h squared is h. So we end up with a final answer of c squared h over 3 units cubed. In part 2, we are told that x starts to increase at a rate of 3 units per second. This increase will cause s of x to increase as well. We must find the rate of change of s of x with respect to time at the instant when x is half the perpendicular height of the pyramid. This is a related rates question, and there's 3 quantities of interest here: x, s of x, and t, the time in seconds. We are asked to find ds dt, the rate of change of s of x with respect to the time t. The first line in the question tells us that dx dt, the rate of change of x with respect to t, will be 3. On the previous page, we were given an expression for s of x. It's equal to x squared c squared divided by h squared. This can be rewritten as c squared over h squared times x squared. If we differentiate this expression, we can find the rate of change ds dx. C squared over h squared is a constant. When we differentiate, this will simply remain on the side. To differentiate the x squared, we multiply down by the power, then reduce the power by 1. This gives us 2x. Combining this into a single fraction gives us 2xc squared over h squared. So, we need to find ds dt. If we multiply above and below the line by dx, we can rephrase this in terms of the two derivatives we just found. ds dt is equal to ds dx times dx dt. We found that ds dx is equal to 2xc squared over h squared. And we found that dx dt is equal to 3. Since 2 times 3 is 6, we end up with 6xc squared divided by h squared. We need to consider the instant when x is half the perpendicular height of the pyramid. Well, h represents the perpendicular height, so half of this would be h over 2. So we'll want to take our derivative and sub in x is equal to h over 2. 6 divided by 2 is 3. And the h above the line will cancel with one of the h's below the line. This brings us to a final answer of 3c squared over h square units per second.